Today we talk about geometric view of infinite series. It's based on an article published in 1985 in the Mathematics Teacher Journal. I'll put a link down below. Let's say R is a number between 0 and 1 and S is an infinite series equal to 1 plus R squared plus R cubed and so on. This is a geometric series because the ratio of any two successive terms is a constant number, in this case R. In order to find the value of this series, we start by a coordinate system. The origin is at point A. We find point B, 1 unit to the right side of point A, and then we draw a line at 45 degrees. We also draw a line perpendicular at point B with length R. If you connect the end of this segment to point A and you extend it, it's going to cross the first line at point C. Because R is less than 1, the slope of this new line AC is less than 45 degrees, and as a result is going to cross the first line. Now, if you go horizontally from the end of the segment, this horizontal segment is also R because you have a 45-degree angle. Now, if you go up, it's going to be R squared because all these right angle triangles are similar and the ratio of the sides is always R. Going horizontal, you have again R squared, vertical you have R cubed, and you continue like that until you converge at point C. Now the horizontal segment on the horizontal axis is S, the series that you have. The first part of it is the segment AB, which has the length equal to 1, and of course the rest of it is S minus 1. The vertical segment from point C is also equal to S minus 1 because it's in front of a 45-degree angle. Now look at this yellow triangle and also this green triangle. They are similar. As a result, the ratio of their sides is the same. So you can write R over S minus 1 is the same as 1 over S. From that, you find S equal to 1 over 1 minus R, which is the value of this infinite series. But what happens if R is bigger than 1? In this case, as you can see, the two lines are not going to cross each other, and the distance between them is going to be larger and larger. So in this case, the series is not going to converge and it goes to infinity. Now let's see a different case. R is still between 0 and 1, but the series S is switching signs. S is equal to 1 minus R plus R squared minus R cubed and so on. We again start by the coordinate system and point B at 1 unit to the right side of A. But this time we draw the line of 45-degree angle downward, as you can see. Then from point B, we go down as much as R and we connect it to point A. We go from point C horizontally. The length of this line is again equal to R because it's in front of a 45-degree angle. From there you go up and the length is going to be R squared because the ratio of the sides of the right angle triangles always is going to be R. Then we go horizontally to the right and we go on a spiral until we converge in the middle. If you draw a perpendicular line from the converging point, you can see that the coordinate of this point is in fact the value of the series S, because it's 1 minus R plus R squared and so on. The rest of it is 1 minus S, which is equal to the vertical distance of this converging point from the horizontal axis. Now look at this yellow triangle and this green triangle. Again, they are similar and the sides have the same ratio. So R divided by 1 minus S is equal to 1 over S. And from that, you get S equal to 1 over 1 plus R. Let's consider this geometric series. We start by a square, and we divide this square into 4 equal segments. We take one segment and again divide it into 4 equal segments, and we continue forever. If from each side of the squares we color only one of them, we can see that we have 3 big squares and then 3 smaller squares and then 3 smaller squares, and from each level, one is colored in purple and 2 are not colored. So you can say that in total, 1/3 of the total square is going to be colored, and that is the value of this series S. What is interesting is that Archimedes used exactly this method to find the area of a parabolic segment. He needed to evaluate this series to find the area of a region enclosed by a parabola and a line that you can see here. That's why he's considered a genius in the history of mathematics. Now this time let's consider this series. Again we consider this square, but this time we divide it into 9 equal segments. And then we take one of those segments and divide it again into 9 segments, and we continue forever. For each side of the squares, we color 4 of them. We have 8 from each side, and half of them are going to be colored. And as you can see, the area of the colored portion is going to be equal to the series S. So S is going to be half. Let's move on to something a bit more difficult. This one is not a geometric series because the ratio of the successive terms is not constant, but still we can use a geometric method to evaluate this series. Let's consider S equal to first this portion, and then we add this portion, and then we add this portion, and so on. As you can see, we have 1/4 2 times, so it's gonna be 2/4, which is what we have in the original series. We have 1/8 3 times, and that's 3/8. The same for all the other ones. Now let's evaluate the first series. We assume this rectangle, it's half plus a quarter plus 1/8 plus 1/16 plus 1/32 and so on. As you can see, it adds up to 1, the whole area of the rectangle. We do the same thing for the second row, it's going to be half. Then the third row is going to be a quarter, and we continue like that. Now if you look at the numbers in the red frame, you can see that it's again equal to 1/2 plus a quarter plus 1/8 plus 1/16, which is what we already evaluated. This is going to be 1. So the total amount of the series S is 1 plus 1, or equals to 2. I hope you enjoyed this video, and thanks for watching.